Today I'm going to talk about climate change. I would like to draw your attention to a couple of key facts. I know that there are many people that are climate deniers, and I think part of that is a consequence of the way the whole issue is framed early on. Initially, there were discussions of global warming, and that is certainly one component of climate change, but it is only perhaps the most obvious component. And of course, every time you have a winter and things get cold, then it's hard to think very much about global warming. And of course, the other point is that when it's winter here in the northern hemisphere, it's going to be summer in the southern hemisphere. So I think it's a difficult concept for many people to comprehend. There's the famous episode of the senator walking under the Senate floor during a discussion of climate change or global warming, bringing in a snowball and using that as a prop to suggest that there was no such thing as global warming. Let's, however, look at some of the data, and all of the data that I'm going to show you, all of the graphs that I'm going to show you today are derived straight from NASA. So much of this data is derived from either satellite imagery or from ice sheets or other sorts of data sources that are extremely reliable. The first of these that I'd like to look at is the atmospheric carbon dioxide. There is a direct relationship between carbon dioxide and temperature anomalies, and we'll look at that in just a few moments. But here we have, based on ice sheets or ice cores, we have a good index of what the atmospheric CO2 has been over at least the last roughly 900,000 years. So that's almost a million-year time frame. And if you look at this graph, you'll notice that there are these pulses of increased CO2 in the atmosphere. And those pulses occur roughly at about cycles of 100,000 years. Those correspond directly with what are referred to as Milankovitch cycles. Milankovitch cycles are the wobbles in the rotation of the Earth. So you can imagine the Earth as being a top spinning on its axis. But as the top slows down, it begins to wobble a little bit, and the Earth is doing exactly the same thing. So it's wobbling on its axis. And those wobbles take about 100,000 years. So during part of that wobble, the Earth is tilted slightly differently than it is during the other parts of the wobble. And because of the changes in photosynthesis on the planet, that then results in these Milankovitch cycles, or these peaks in CO2. But if you look at the graph, you'll notice that there's sort of an unfortunate event that occurs, and it's roughly about 1950. So it's roughly at one of the peaks of these Milankovitch cycles. And there you see that it doesn't go back down. But starting in about 1950, there's this precipitous increase in CO2, atmospheric CO2 levels. So the current level is where we are today in 2020. And you can see the dramatic change since 1950. If that doesn't give you pause, then I'm not sure anything will. But that is a pretty significant change. Now, if you think about what's happened historically and what might be driving that, there are a couple of things. One is the rather dramatic increase in population size. So since 1950, the population on the planet has more than doubled. And of course, the other thing was both the Industrial Revolution and the assembly line, which brought us the automobile. So back in the early part of the 20th century, automobiles were not very abundant. But by 1950, there was, I think, most people in the United States, other than perhaps in New York City or some of the major cities, had automobiles. And of course, now it's exacerbated because whereas in 1950, most people had one automobile. Today, most households have multiple automobiles together with their motorhomes and their lawn tractors and their boats and whatever else. So the number of people that are using resources, using fossil fuels, generating CO2 has increased. The number of people driving, or the total miles driven, has increased rather dramatically. And both of those things contribute to these increased CO2 levels. So here now you can see what those temperature anomalies look like. So what I mean by an anomaly is a deviation from the average. And the dark line on this graph is a moving average. So it's averaged over the previous years, and I'm not sure exactly how many years these are averaged over, but you can see the trend. And if you look at this since 1880, which, by the way, is when temperature data was first started to be recorded in a systematic fashion, and of course today there are weather stations essentially at every airport and in every small town. There are NOAA weather stations that record temperatures on a daily basis. So you can average those both across large geographic areas and across the globe, and that's what you see here. And these temperature anomalies then are the deviations from those moving averages. And you can see two things. First of all, the temperature anomalies are increasing with time, right? So the anomalies are going to be both above and below. If there were no temperature anomalies, that is, if we were just continuing at the average temperature for the season, for the year, and so on, everything would be a horizontal line at zero. But the fact that we are increasing above and consistently above is the part of this whole equation that is concerning. So this only dates back to 1880, and of course we recognize, based on the CO2 levels, that it actually goes back somewhat farther than that. Let's look graphically at what's happened to temperatures over roughly the last 100 years or so. And I think this graphic illustrates that pretty nicely. The warmer the colors, the warmer the temperatures relative to the long-term running average. And you can see that across here that with the passage of time, the globe is getting warmer and warmer and warmer. Notice that we're only talking about a difference of roughly 4 degrees Fahrenheit, 8 degrees Fahrenheit from the lowest to the highest over the last 120 years or so, 140 years. But that's still quite dramatic. And you can see that by today, right, in the year 2020, that the globe is a much warmer place than it was just a short 140 years ago. Now, if you look at direct measurements of CO2 in the atmosphere, and this is just over roughly the last 13, 14, 15 years or so, you can see that the amount of CO2 in the atmosphere is increasing rather dramatically. So this is within your lifetime. That the amount of atmospheric CO2 has increased pretty consistently. Of course, now with the pandemic in full swing, you could fully expect that there's going to be a dip in that, in the amount of CO2 generated, just because of reduced industrial production, less travel by people, and so on. But the overall trend is concerning. It is increasing. And that has to make you think a little bit. What you might consider is what happens to all of that CO2 and why is it a problem? Well, the good news is if you're a plant, you have an abundance of gases that you need. Plants, of course, depend on CO2 for photosynthesis. And one of the waste products of plants is oxygen, and that's what we require. So the plants are in good shape, right? They're getting all of the CO2 presented to them. Of course, the downside is that we are deforesting the planet at a pretty rapid rate. So the total amount of photosynthesis that's taking place on the planet is not necessarily increasing, which is, of course, exactly what we need. We need more photosynthesis to absorb or to sequester that carbon dioxide, not less. Here again is the same slide that you saw initially without the pretty background, right? So this is just based from ice cores and the amount of atmospheric CO2 And again, you can see that precipitous increase beginning in about 1950. Looking at this graphic of atmospheric CO2 since 2002, notice what happens, especially just within the last few years. The darker colors or the warmer colors indicate higher atmospheric concentrations of CO2, going up well over 400 parts per million. One of the consequences of increased CO2 in the atmosphere is that this layer of CO2 actually traps heat and light underneath the atmosphere, so that less of the light, less of the heat is escaping back out into space. You can think of it as a nice warm comforter being draped over the planet. So the consequence of that then is that in a very subtle way, the temperatures on the planet are increasing, not by much, but they are increasing a little bit, perhaps only a few degrees at a time, or a fraction of a degree at a time. But that's sufficient to begin this process of melting the ice caps and the glaciers. There are two major ice caps, right? The Arctic ice caps and then the Antarctic ice caps. And the extent of those, the extent of that total amount of ice on the planet has been decreasing. So just these subtle changes in temperature over the last century or so has resulted in melting of those ice caps. And you can see from this graphic that basically since something like 1976 or 1975, we've gone from roughly a minimum of 7 million square kilometers of ice down to just about 4 million square kilometers. So there is essentially the minimum extent of those ice caps, that is during the summer, is about half of what it was just 50 years ago or so. So it's that is pretty scary, I think. The rate of change for the total ice on the planet is about 13% per decade. If you look at the amount of change in billions of metric tons per year, it's about 149 billion metric tons per year of ice that are lost. And for the Antarctic, you can see that in the graphic here. There's a gap in the data, and that's simply a function of the loss of a particular mission, satellite mission, that's since been restored. But the trend is pretty clear, right? So the total ice mass in the Antarctic has decreased pretty dramatically just within your lifetime. If you look at what's happening in Greenland, it's the same picture. Here, the rate of change is about 279 billion metric tons per year. Again, it's the same pattern. And this, again, is just during your lifetime. Just within the last decade or so, if you were to go to Greenland, you would see significant evidence of loss of the ice sheets, and you can see that in this time-lapse video here, illustrating rather dramatically the loss of ice across this far northern continent. It is stunning. You can look at the foreground and you can see the retreat of the ice there. And using time-lapse, you can see the actual flow of the ice from the higher elevations down to the sea. Here is a graphic illustrating what's been happening to the Arctic ice sheet just since the late 1970s through to the present. And it is pretty dramatic. The one thing that I would like to point out is that initially there was no passage through that ice sheet. I mean, you could use icebreakers and so on, but it was a pretty perilous sort of activity. Now, of course, the situation is such that the Soviet, or the Russians, no longer the Soviets, but the Russians are out there exploiting that what is now an open sea, and they're using that for military purposes and so on. And you can see that the northern part of our country is now exposed. Certainly, Canada and Alaska are exposed to access to the Soviets. And you'll recall that the North Shore of Alaska is rich in oil, and of course the Soviets would like to exploit that. So there are defense issues that need to be addressed, and of course there are the petroleum reserves that need to be considered. Of course, the other thing to keep in mind is that the ice sheets are not devoid of life. They are teeming with seals and polar bears and lemmings and snowshoe hare. All sorts of organisms live on those ice sheets. And of course, as you probably know about polar bears, they are not doing well as a consequence of the loss of that ice sheet. So that's the implication is clear. There's a lot of ice that is melting, and there are a couple of consequences of that melting ice. One consequence is that that ice then becomes available to the ocean, and sea levels are then rising. And you can see that in this graphic here, which again is roughly over your lifetime. It's an increase in the sea level by about 3.3 millimeters per year. Well, that's not a lot, right? That's relatively minor. But if you accumulate that year after year after year, you get this particular trend, which is pretty significant. So 100 millimeters, that's already a fair increase in the amount of sea level. There are already some land masses, some island land masses in Southeast Asia that are on the verge of being completely inundated. So this is not a trivial. If instead of relying on satellite imagery, you actually rely on tide records that are recorded on the ground, you can go back quite a bit farther. You can go back all the way to 1880. And there you can see that since 1880, so roughly 140 years ago or so, there's been an increase of roughly 250 millimeters, which again is actually quite a bit. Now we could look for physical evidence across the globe, and I'm just going to use one example here, and this is from in Montana. I believe this is in Montana. This is at Glacier National Park. There is if you've never been to Glacier National Park, you should go pretty quickly, because this particular glacier is essentially not there anymore. I mean, there is a small bit of ice still extant, but it is nothing at all like it was when I was a kid. So here's a photograph taken at the same location from 1898 and comparing that with 2003. Of course, that was 17 years ago, and the extent of ice has increased rather dramatically since then. So if you'd like to see glaciers within the continental United States, I suggest that you go as soon as you possibly can, because you won't see them perhaps in 5 or 10 years. They will be gone. Looking at the effects of what the increased CO2 concentrations have on, in particular, sea level change, let's look at this graphic. Here's what happens, and this is just for the southeastern United States, with every 1 meter increase in sea level. So you'll notice that initially we lose New Orleans, followed by the Keys and Miami, parts of South Carolina, Georgia, North Carolina, So there is going to be a significant loss in those coastal cities with rises in sea level. You could look at the Pacific coast and see the same sorts of effects. Some would argue that that's not a bad thing. It wouldn't bother me too much if Los Angeles, Long Beach, Torrance, and so on were to disappear under the waves, but I'm sure the people that live there wouldn't be all that happy.